The most beautiful thing in the universe is something you've never seen with your eyes. Not with your naked eyes, at least. Not standing on Earth, looking up at the night sky because human vision is limited. We evolved to see a narrow slice of reality, the visible spectrum, the wavelengths between red and violet. We see sunsets, mountains, oceans, forest, faces. And yes, these things are beautiful, but they're nothing compared to what's out there. The universe contains beauty so extreme, so alien, so utterly beyond human scale that it breaks our concept of what beautiful even means. Storms larger than Earth, raging for 3 centuries. Towers of gas and dust, trillions of miles tall, where stars are being born. Galaxies containing 1 trillion suns spinning in perfect spirals shaped by gravity alone. Dead stars exploding and leaving behind glowing monuments to their own destruction. These aren't artists' conceptions, they're not CGI, they're not fiction, they're real, photographed, measured, studied. 10 objects so spectacular, so perfect, so breathtakingly gorgeous that they'll change how you see the cosmos forever. By the end of this journey, you'll understand something profound. The universe isn't just scientifically interesting. It isn't just a collection of rocks and gas following physical laws. It's an art gallery, a museum of wonders, a masterpiece painted across billions of light years. And the admission is free. You just have to look up, let's begin. But first, we need to ask a fundamental question. What makes something beautiful? Is beauty subjective, purely in the eye of the beholder? Or is there something objective about it, something universal? Philosophers have debated this for millennia. Plato argued for objective beauty, perfect forms that exist independent of observers. Hume argued the opposite. Beauty exists only in the mind, perceiving it. In the cosmos, beauty correlates with physics. Symmetry, complexity, harmony, pattern, scale, color, structure. When an object exhibits perfect mathematical symmetry, like a spiral galaxy, we recognize it as beautiful. When colors blend and contrast in unexpected ways, like a nebula glowing red and blue, we feel awe. When something operates at a scale so vast we can barely comprehend it, like a galaxy cluster, we experience sublimity. The universe creates beauty automatically as a byproduct of physics working correctly. Gravity sculpts spiral arms, magnetic fields shape nebulae. Nuclear fusion creates color, chemistry paints surfaces. Beauty isn't decoration. Beauty is the signature of natural law. And we're about to rank the top 10 most beautiful objects in the universe based on 3 criteria. 1. Visual impact. How does it look? Color, structure, composition, symmetry. 2. Scientific significance. What does it teach us? What processes created it? What does it reveal about the universe? 3. Emotional resonance. How does it make you feel? Does it inspire awe, wonder, humility, connection? Some objects on this list you've probably seen before, iconic images from Hubble or NASA. Others might be new to you, but all of them share one thing in common. They're so beautiful they almost don't seem real, and yet they are real, more real than anything humans have ever created. Here's how this journey works. We're going to count down from number 10 to number 1, each object more spectacular than the last, each pushing the boundaries of what beauty means. We'll start close to home, objects in our own solar system that you could theoretically visit with spacecraft. Then we'll venture into deep space, nebulae light years across, galaxies millions of light years away. Phenomena operating at scales that make planets look like dust specks. By the time we reach number 1, we'll be confronting images that contain not just one beautiful object, but thousands. Images that peer back through time itself, showing us the universe as it was billions of years ago. And here's what I want you to understand as we go. These aren't just objects. They're not just things floating in space. They're masterpieces, created not by artists, but by gravity, nuclear fusion, magnetism, chemistry, and time, created by the same physical laws that govern everything from atoms to galaxies. The universe is a master sculptor, a painter working with plasma and dust, an architect designing on scales we can barely imagine. And we, tiny, fragile, short-lived creatures on a small planet, have the privilege of witnessing its work. Some of these objects have existed for billions of years, shining in the darkness long before humans evolved, long before Earth itself formed. They were beautiful then, even with no eyes to see them, and they'll be beautiful long after we're gone. But right now, in this moment, you get to see them. You get to experience cosmic beauty that your ancestors could only dream about. Telescopes have given us eyes beyond our evolution. We can see infrared, ultraviolet, X-rays, radio waves, the entire electromagnetic spectrum translated into colors our brains can process. We can zoom in on details billions of miles away. We can watch stars being born and stars dying. We can see the architecture of space-time itself, bending around black holes. This is your universe, not just astronomers, not just scientists, yours. You're made of the same atoms as these nebulae. Your body contains iron forged in dying stars. You are literally stardust, organized into a pattern complex enough to appreciate beauty. And now, you're about to see what the universe can do when it really wants to show off. Let's start the countdown. Let's start our countdown with something familiar. An object so iconic, it's become synonymous with space itself. Number 10. Saturn's rings. When Galileo first pointed his crude telescope at Saturn in 1610, he saw something strange. The planet appeared to have ears, bulges on either side that made no sense. His telescope wasn't powerful enough to resolve the true shape. It wasn't until 1655 that Dutch astronomer Christiaan Huygens realized the truth. Saturn is surrounded by a ring not attached to the planet, not solid. A ring floating in space encircling the planet like a halo. And when we finally sent spacecraft to visit, Pioneer 11, Voyager 1 and 2, and most spectacularly, Cassini, we discovered something even more beautiful than early astronomers imagined. The rings aren't one continuous disk. They're thousands of individual ringlets, each composed of billions upon billions of chunks of water ice, ranging in size from grains of sand to houses, all orbiting Saturn independently. From a distance, they appear solid, a smooth, bright band wrapping around the planet. But up close, they reveal intricate structure, gaps carved by shepherd moons, braided sections where gravitational resonances twist the orbits, waves and ripples propagating through the ice like water. The colors are subtle but gorgeous, mostly white and grey, pure water ice reflecting sunlight. But there are hints of pink and gold where organic compounds and rocky dust contaminate the ice. There are shadows, deep black bands where Saturn itself blocks the sun's light, casting its shadow across the rings. And here's what makes them truly beautiful. They're impossibly thin. The rings stretch nearly 300,000 kilometers from edge to edge, wider than the distance from Earth to the Moon. But vertically, in some places, they're only 30 feet thick. Imagine taking a piece of paper the size of a football field and standing it on edge. That's the proportions we're talking about. The rings are essentially two-dimensional, a flat disk of ice orbiting Saturn with almost no thickness at all. When the rings are edge-on from Earth's perspective, which happens every 15 years or so, they practically disappear. They're so thin that even large telescopes can barely see them. The Cassini spacecraft gave us the final, definitive images of Saturn's rings. For 13 years it orbited the planet, photographing the rings from every angle. And in September 2017 it made its final dive, plunging through the gap between Saturn and the rings, sending back data until the very last second before burning up in Saturn's atmosphere among Cassini's final gifts, images of the rings backlit by the sun. With the sun behind them, the rings become translucent. Individual particles sparkle like diamonds. The structure becomes three-dimensional. You can see through the gaps, watch shadows play across the particles, observe how light scatters through ice. It's one of the most beautiful images ever captured by a spacecraft. Saturn's rings glowing like jewelry, lit from behind, revealing their delicate structure against the blackness of space. But here's the bittersweet part. The rings are temporary. Current estimates suggest Saturn's rings are only 100 to 400 million years old. Young, cosmically speaking. Gravity is slowly pulling ring particles down into Saturn's atmosphere. In another 100 million years, maybe less, the rings will be gone, vanished. Saturn will be just another gas giant, stripped of its crown. Future humans, if they exist, won't see Saturn's rings. They'll look at our photographs the way we look at illustrations of extinct animals, marveling at something that once existed but is gone forever. We live in the brief cosmic moment when Saturn has rings, and we're fortunate enough to have spacecraft that can show us their beauty in exquisite detail. That's number 10. An object in our own cosmic backyard, visible through a backyard telescope. A reminder that even among the familiar planets, there's beauty profound enough to take your breath away. But Saturn's rings are just the beginning. Number 9. Jupiter's Great Red Spot. If Saturn's rings are delicate and intricate, Jupiter's Great Red Spot is the opposite. Massive, raw power made visible. It's a storm. An anticyclonic hurricane spinning counterclockwise in Jupiter's southern hemisphere, and it's been raging for at least 350 years. We know this because the first confirmed observation was in 1831, though some astronomers believe sketches from the 1660s show the same feature. That means this storm has persisted longer than the United States has existed, longer than the Industrial Revolution, longer than most nations on Earth, and it's big. At its largest extent, measured in the late 1800s, the Great Red Spot was approximately 40,000 kilometers across. That's more than 3 Earths wide. Earth's diameter is about 12,700 kilometers. So the spot at its peak could have fit 3 Earths side by side with room to spare. Today, after more than a century of shrinking, it's about 15,000 kilometers across, still larger than Earth, but only about 1 Earth width now rather than 3. The storm is dying, slowly but measurably. Imagine a storm so large that entire planets are dwarfed by it. Wind speeds at the edge reaching 400 to 500 kilometers per hour, stronger than the most powerful hurricanes on Earth clouds, swirling in complex patterns. Smaller storms being torn apart and absorbed, lightning flashing in the depths. The color is what makes it truly distinctive. Deep red, rust-colored, sometimes orange or pink. The exact chemistry is still debated. Possibly phosphorus dredged up from Jupiter's lower atmosphere, possibly organic compounds created by ultraviolet light, possibly sulfur in some exotic form. But whatever causes it, the red stands out dramatically against Jupiter's pale yellows and whites. It's like a wound on the planet's surface, a crimson eye staring out at the cosmos. When Voyager 1 and 2 flew past Jupiter in 1979, they captured close-up images that revealed the spot's inner structure. It's not a solid mass of color, it's layers, swirls within swirls, turbulence at every scale. The edges are sharp and defined where the storm meets Jupiter's jet streams. The interior shows complex convection patterns. More recent images from the Juno spacecraft, which has been orbiting Jupiter since 2016, show even more detail. Juno passes within a few thousand kilometers of Jupiter's cloud tops every 53 days, and its camera captures the Great Red Spot from angles never before possible. These images reveal something both beautiful and unsettling. The storm is shrinking. In the 1800s, the spot was 40,000 kilometers wide. By 2014, it was 16,500 kilometers. By 2020, about 15,000 kilometers. It's losing roughly 1,000 kilometers of width every decade. At this rate, within the next 20 to 40 years, the Great Red Spot might transform into the Great Red Circle, more compact, possibly more intense. Or it might dissipate entirely, vanishing after centuries of persistence. We don't know why it's shrinking. We don't fully understand what sustains it in the first place. Jupiter's atmosphere is alien, hydrogen and helium, pressures millions of times Earth's surface pressure, no solid surface to provide friction and dissipate energy. On Earth, hurricanes need warm ocean water to sustain them. When they make landfall, they die within days. But Jupiter has no land. There's nothing to stop a storm except other storms, competing for energy and momentum. The Great Red Spot has survived for centuries because it's incredibly stable. It's locked between two jet streams, one flowing eastward to the north, one flowing westward to the south. These jets act like railway tracks, keeping the storm contained and preventing it from drifting or dissipating. But something is changing. Maybe the jet streams are shifting. Maybe smaller storms are siphoning off energy. Maybe Jupiter itself is evolving in ways we don't understand. Whatever the cause, we're watching it happen in real time. A storm that has raged since before the invention of photography is now dying before our eyes. And here's what makes it beautiful, beyond just the visuals. It's a reminder that even the most permanent seeming things in nature are temporary. Even storms that dwarf planets eventually fade. Jupiter's Great Red Spot is a colossal storm, turbulent, chaotic, and endlessly dynamic. But it's also order. A stable structure emerging from instability, beauty born from destruction. It's proof that the universe can create art, even in its most hostile environments. That's number 9. A storm you can see through a backyard telescope. A small, red oval on Jupiter's disk, but a storm that contains more energy than every hurricane on Earth combined. A storm that has outlived empires, and it's slowly fading away. Number 8. Earth's aurora. We've looked at other worlds. Saturn with its rings, Jupiter with its Great Red Spot. Now, let's come home. Because Earth has its own beauty, and it's something you can experience directly, not just see in photographs. The Aurora Borealis in the Northern Hemisphere. The Aurora Australis in the south. Dancing curtains of light that shimmer across the polar skies, visible on dark, clear nights when conditions are just right. Green mostly, the most common color, created when solar wind particles collide with oxygen atoms at altitudes of 100 to 300 kilometers. But also red, high-altitude oxygen, purple and blue, nitrogen, and occasionally pink, a mix of colors at different altitudes. The aurora moves. It ripples like fabric blowing in wind. It pulses in brightness. It forms arcs and spirals and rays that seem to emanate from a single point high overhead, the magnetic north or south pole. Ancient cultures saw the aurora and created myths. The Norse believed it was light reflecting off the shields and armor of the Valkyries. The Inuit believed it was spirits playing a game with a walrus skull. Medieval Europeans sometimes interpreted red auroras as omens of war or disaster. But the truth is more beautiful than the myths. The aurora is what happens when Earth's magnetosphere, the invisible magnetic field surrounding our planet, interacts with the solar wind. The sun constantly streams charged particles into space. This solar wind, mostly protons and electrons, travels at speeds of 400 to 800 kilometers per second. When it encounters Earth's magnetic field, most of it is deflected around us, like water flowing around a rock in a stream. But at the poles, where the magnetic field lines converge and point downward into the atmosphere, some particles follow those field lines and funnel into the upper atmosphere. When these high-energy particles collide with atoms in the atmosphere, oxygen and nitrogen, they transfer energy. The atoms become excited, electrons jumping to higher energy levels. When the electrons drop back down, they release that energy as photons, light. Different atoms release different colors. Oxygen produces green and red. Nitrogen produces blue and purple. The altitude determines which atoms are present and how much energy the collisions carry. The result: glowing curtains of light that follow Earth's magnetic field lines. The aurora appears at high latitudes because that's where the field lines guide particles into the atmosphere, and the aurora is dynamic because the solar wind is dynamic. When the Sun releases a coronal mass ejection, a massive burst of plasma and magnetic field, the solar wind intensifies. More particles reach Earth. The aurora becomes brighter, more active, more widespread. During powerful geomagnetic storms, the aurora can be seen far from the poles. In 1859, during the Carrington event, the most powerful solar storm in recorded history, aurora were visible as far south as Cuba and Hawaii. The lights were so bright people could read newspapers by them at midnight. Modern aurora displays, captured by time-lapse photography, are mesmerizing green curtains ripple across the sky. Vertical rays appear and disappear within seconds. The entire sky pulses with light, like the Earth itself is breathing. And here's what makes the aurora special compared to everything else on this list. You can stand beneath it. Not just see it in photographs, not just observe it through telescopes. You can physically go to the auroral zones, northern Norway, Iceland, Alaska, northern Canada, Antarctica, and watch the lights with your own eyes. People plan entire trips around aurora viewing. They travel thousands of miles. They wait in freezing temperatures in the middle of the night. They watch the sky for hours, hoping for a display. And when it happens, when the sky comes alive with color and motion, it's transcendent. Because you're not just watching light, you're watching the sun paint the atmosphere with charged particles. You're seeing the invisible made visible, magnetic fields, solar wind, atmospheric chemistry, all combining to create beauty. You're watching physics become art. Every photon of aurora light is a tiny story. A particle traveled 150 million kilometers from the Sun, got channeled by Earth's magnetic field, collided with an oxygen atom at 200 kilometers altitude, and released its energy as green light that entered your eye and triggered neurons that interpreted it as beauty. That's what you're seeing. The universe showing off. Right here on Earth. The aurora reminds us we don't need to travel to distant nebulae or alien planets to experience cosmic beauty. It's here. Above our heads, visible to anyone willing to venture to high latitudes and look up. That's number 8. Earth's aurora, the universe painting our sky with light. But as spectacular as the aurora is, it's just the beginning. We're still in our solar system, still among objects we can visit with spacecraft. Now, we venture deeper, into regions measured in light years rather than kilometers, into clouds of gas where stars are being born and stars are dying, into the nebulae. We've seen beauty close to home, rings, storms, lights in our own atmosphere. But now we step beyond planets, beyond anything human spacecraft have visited, into the realm of deep space, where beauty operates on scales that dwarf entire solar systems. Let's continue. Number 7. The Pillars of Creation. If you've ever seen a top space images list, this one was on it, probably near the top. Because the Pillars of Creation are arguably the most iconic photograph in the history of astronomy. Taken by the Hubble Space Telescope in 1995, this image shows 3 towering columns of gas and dust rising from a larger nebula. The Eagle Nebula, located about 6,500 light-years away in the constellation Serpens. But calling them pillars doesn't do them justice. These aren't architectural columns, they're not static or stable, they're enormous, actively eroding star-forming regions where new suns are being born inside cocoons of cold molecular gas. Let me give you the scale, because the scale is what makes this incomprehensible. The leftmost pillar, the tallest one, is approximately 4 light-years from base to tip. 4 light-years. That's almost the distance from our Sun to Proxima Centauri, the nearest star that's 38 trillion kilometers. That's a distance so vast that light itself, traveling at 300,000 kilometers per second, takes 4 years to cross it. And that's just one pillar, one column in this image. The entire Eagle Nebula spans about 70 by 55 light-years. If you were standing at the base of one of these pillars looking up, you wouldn't see the top. It would be light-years away, hidden by the dust and gas between you and it. The pillar would extend beyond your vision, beyond your ability to comprehend. But from our perspective, 6,500 light-years away, we see the entire structure. And it's breathtaking. The colours in the famous 1995 image are subtle. Deep reds and oranges at the base, fading to dark brown and black in the shadowed regions, with bright young stars glowing like jewels embedded in the tips. But in 2014, Hubble revisited the pillars with newer, more sensitive cameras. The new image reveals far more detail. You can see texture in the gas, ripples, waves, dense knots where material is collapsing. You can see evaporating gaseous globules or small, dense pockets of gas that are collapsing to form new stars. And you can see the erosion. The pillars aren't static, they're being destroyed. Just outside the frame of the iconic image, there's a cluster of massive, young, hot stars. These stars formed recently from the same nebula, and they're incredibly bright, pumping out intense ultraviolet radiation that ionizes and heats the surrounding gas. This ultraviolet light is literally eating the pillars. Photons strike the surface of the columns, ionizing hydrogen atoms, heating the gas, causing it to evaporate and stream away into space. This process is called photoevaporation, and it's sculpting the pillars, carving them into the dramatic shapes we see. The pillars aren't growing, they're shrinking, being eroded by starlight. Finger-like protrusions point toward the hot stars, created by denser clumps of gas that resist evaporation longer than their surroundings. It's like watching a sandcastle slowly dissolve as waves wash over it, except the sandcastle is light-years tall and the waves are made of ultraviolet photons. Inside the densest parts of the pillars, where the gas is thick enough to block the radiation, new stars are forming. Gravity pulls gas together. The clumps collapse, heat up, ignite nuclear fusion. Stars are born. Some of these protostars are visible in infrared images, glowing red embers buried inside the columns. They're only a few 100,000 years old, babies, cosmically speaking. Some haven't even begun fusing hydrogen yet. They're still contracting, still heating up. Pre-main sequence stars called T Tauri stars. In a few million years, these stars will emerge from their dusty cocoons, blowing away the remaining gas with stellar winds. They'll join the cluster of young stars nearby, becoming part of the next generation illuminating the nebula. But here's the heartbreaking part. The pillars of creation are probably already gone. In 2007, astronomers using the Spitzer Space Telescope detected infrared evidence suggesting a supernova may have exploded in the Eagle Nebula region roughly 6,000 years ago. If this interpretation is correct, and it remains debated among astronomers, the shockwave from that explosion could potentially have disrupted or destroyed the pillars. But we're 6,500 light-years away. We're seeing the pillars as they were 6,500 years ago, when humans were just inventing agriculture, just beginning to build the first cities. Whether they still exist today, we won't know for certain until light showing their current state reaches us in about 500 years. We may be seeing a ghost, a beautiful, intricate structure that might no longer exist, or the pillars might have survived. The uncertainty itself is humbling. Preserved in light, traveling across the cosmos, a photograph of something that was destroyed millennia ago but remains visible because of the vast distances involved, and that somehow makes it more beautiful, more precious, because we're witnessing something lost. A monument that stands in light even though the reality crumbled ages ago. The pillars of creation teach us that beauty is temporary, that even structures trillions of miles tall eventually fall, that creation and destruction are intertwined, always, everywhere in the universe. Stars are born. Stars destroy their own birthplaces. New stars form from the debris. The cycle continues, and we, tiny, short-lived, fragile, get to witness one moment in that cycle frozen in a photograph. Preserved forever. That's number 7, Towers of Creation. Monuments to birth and death. Pillars standing in the darkness, slowly eroding, doomed but defiant beauty captured in the act of vanishing. Number 6, the Helix Nebula. If the pillars of creation show us stellar birth, the Helix Nebula shows us stellar death. This object has many names. Its catalogue designation is NGC 7293. Astronomers call it a planetary nebula. Not because it has anything to do with planets, but because early observers thought these round, disc-like objects resembled planetary discs, a giant eye staring back at us from 650 light-years away. An iris of red and orange gas surrounding a bright blue-white pupil, the dying star at the centre. The structure is hauntingly beautiful. The outer shell is roughly circular, tinged with red and orange from ionized nitrogen, and hydrogen delicate filaments extend radially outward from the centre, like blood vessels in an eye. The inner region is dominated by blue and green. Ionized oxygen, heated to over 10,000 Kelvin by the central star's ultraviolet radiation. And at the very centre, the star itself. A white dwarf, the exposed core of what was once a sun-like star, now stripped of its outer layers, glowing at a surface temperature of 120,000 Kelvin. Let me tell you this star's story. Because the Helix Nebula is a biography, written in gas and light. 500 million years ago, when Earth's oceans were filled with the first complex animals, when the Cambrian explosion was creating unprecedented diversity of life, a star, roughly the mass of our Sun, was shining in what would eventually become the constellation Aquarius. It was yellow, stable, fusing hydrogen into helium in its core, pumping out steady energy for billions of years. It may have had planets, it may have hosted life, we'll never know. But stars like the Sun don't live forever. When the hydrogen in the core runs out, fusion stops. Without the outward pressure from fusion, gravity takes over the core contracts. As it contracts, it heats up. Eventually it gets hot enough to ignite a shell of hydrogen around the core. This shell burns furiously, producing more energy than the star produced during its normal lifetime. The extra energy causes the star's outer layers to expand. The star swells into a red giant, hundreds of times its original size, cooler on the surface, but vastly more luminous overall. Our Sun will do this in about 5 billion years. It will expand past Mercury's orbit, possibly past Venus, maybe even reaching Earth. Its outer atmosphere will be tenuous, barely held by gravity, billowing into space. For the star that became the Helix Nebula, this red giant phase lasted millions of years. Its outer layers became unstable. Stellar winds, streams of charged particles flowing from the surface, intensified. Material began streaming away from the star, lost into space. Then, about 10,000 years ago, the end came. The star's outer layers detached completely, blown away by stellar winds and radiation pressure. The layers expanded outward at speeds of 30 to 40 kilometers per second, over 100,000 kilometers per hour. What remained was the core, a white dwarf. An object about the size of Earth, containing about 60% of the Sun's mass, compressed to incredible densities. Matter so dense that a teaspoon would weigh several tons. The white dwarf is hot, 120,000 Kelvin on the surface, compared to the Sun's 5,800 Kelvin. It glows blue-white, pumping out intense ultraviolet radiation. That radiation floods into the expanding shell of gas, ionizing it, making it glow. Different elements produce different colors. Hydrogen glows red, nitrogen glows red-orange. Oxygen glows blue-green. Helium glows faint blue. The result is the structure we see today, a glowing shell of multicolored gas expanding outward, illuminated from within by the dying star at its heart. The Helix Nebula is about 2.5 light-years across. It's one of the closest planetary nebulae to Earth, which is why we can see it in such detail. Hubble images reveal thousands of tiny knots and filaments, dense clumps of gas that survived the initial expansion, cometary knots with heads facing the central star and tails streaming away. Each knot contains as much mass as several Earths. They're being eroded by the central star's radiation, slowly evaporating, leaving trails of gas behind them like cosmic tadpoles. In infrared images, you can see the outer halo, faint shells of gas expelled before the main nebula, earlier mass loss events during the red giant phase. The helix didn't form in a single explosion. It formed in stages, layers of material shed over thousands of years, each expanding at different speeds, creating the complex structure we see. And here's what makes the Helix Nebula profound. It's personal. This is our Sun's future. In 5 billion years, the Sun will exhaust its hydrogen, swell into a red giant, and shed its outer layers. It will create a planetary nebula, probably similar to the Helix. Earth, if it survives the red giant phase, will orbit inside that nebula. Our planet will be bathed in the glowing gas of its parent star's corpse. When we look at the Helix Nebula, we're looking at the Sun's destiny. We're seeing what our star will become, what our solar system will experience. It's a memorial, a gravestone. But it's also beautiful. The Helix Nebula teaches us that death can be as gorgeous as life, that endings, like beginnings, can inspire awe, that even when stars die, they create art. The white dwarf at the center will cool over billions of years, fading from blue to yellow to red to, eventually, black. The nebula will dissipate, its gas mingling with the interstellar medium, becoming raw material for future generations of stars and planets. But for now, for this brief cosmic moment, the Helix Nebula shines. A monument to a star that lived billions of years and died creating beauty, an eye staring back at us. Reminding us, all things end. Make them beautiful while you can. That's number 6. A star's dying breath, frozen in light. Our Sun's future, written in glowing gas. Number 5. The Butterfly Nebula. Also known as NGC 6302, this object takes planetary nebulae to another level entirely. If the Helix Nebula is elegant and symmetrical, the Butterfly Nebula is turbulent, chaotic. Extreme in every measurable way, it looks exactly like its name suggests, a butterfly with wings spread wide, viewed from above. 2 enormous lobes of glowing gas extending in opposite directions from a central star, creating perfect bilateral symmetry. But these aren't delicate butterfly wings, they're furnaces. The gas in the wings is heated to over 20,000 degrees Celsius, 36,000 degrees Fahrenheit. That's 4 times hotter than the Sun's surface. Hot enough to melt any known material instantly, hot enough that atoms are partially ionized, electrons stripped away by the intense heat. The colors are spectacular. Deep reds and oranges at the outer edges where the gas is cooler and less ionized. Moving inward, the colors transition to yellows, greens, blues, indicating increasing temperature and ionization. Near the center, where the star's radiation is most intense, the gas glows brilliant blue-white. The structure is intricate. The wings aren't smooth surfaces. They're filled with knots, filaments, and bubbles. Turbulent gas expanding at different speeds. Shock waves where fast-moving material slams into slower material ahead of it, compressing and heating it. And the scale is staggering. From wingtip to wingtip, the Butterfly Nebula spans about 3 light-years. That's roughly the distance from our Sun to Proxima Centauri. An entire interstellar distance crossed by the wings of a cosmic butterfly. At the center, hidden behind thick dust, is one of the hottest stars known. A white dwarf with a surface temperature estimated at 250,000 Kelvin. To put that in perspective, our Sun's surface is 5,800 Kelvin. This white dwarf is 43 times hotter. It's so hot that most of its radiation is in the extreme ultraviolet and soft X-ray range, wavelengths that don't even register as light to human perception. This star was originally about 5 times the mass of our Sun. When it died, it didn't go gently. But why the butterfly shape? Planetary nebulae come in many forms. Some are spherical like the helix, some are elliptical, some are chaotic and irregular. But many, like the butterfly, are bipolar, with 2 lobes extending in opposite directions. The most likely explanation involves the star's rotation and magnetic field. As the star shed its outer layers, its magnetic field channeled the material, funneling gas along the magnetic poles. The equatorial regions, meanwhile, retained a disk of denser material, dust and gas, that resisted being blown away. The result? Gas flows freely along the poles, creating the wings. The equatorial disk blocks expansion in that direction, creating the narrow body of the butterfly. It's the same physics that creates jets from young stars and from supermassive black holes. Rotating objects with magnetic fields naturally create bipolar outflows. The universe seems to love this geometry. Hubble images of the Butterfly Nebula reveal extraordinary detail. You can see individual fingers of gas extending from the wings, dense clumps that are being accelerated to speeds exceeding 1 million kilometers per hour. You can see bow shocks where fast-moving gas collides with the surrounding interstellar medium. And you can see dust, lots of it. The central region is so thick with dust that the white dwarf itself is completely obscured in visible light. We can only see it in infrared and X-ray wavelengths that penetrate the dust. This dust is rich in carbon and silicates, material forged in the star's core during its lifetime, dredged up during the red giant phase, and now expelled into space. This dust will eventually become part of new molecular clouds, contributing to the formation of new stars and planets. The iron in your blood, the calcium in your bones, the carbon in your DNA, all of it was created in stars like the one that formed the Butterfly Nebula atoms, forged in stellar cores, scattered through space when the star died, incorporated into planets, absorbed by living organisms. You are made of dead stars. And when you look at the Butterfly Nebula, you're looking at the process that created you. The nebula is about 3,800 light-years away in the constellation Scorpius. It's too faint to see with the naked eye or even most amateur telescopes, but professional observatories and space telescopes reveal it in all its glory. And here's what makes it. Number 5 on this list. It's not just beautiful, it's perfect. The symmetry is so exact, so precise, that it seems designed. The 2 wings are mirror images of each other. The colors grade smoothly from edge to center. The structure reveals the physics of dying stars with crystal clarity. Nature created a butterfly, not through evolution or biology, through gravity, nuclear fusion, magnetism, and gas dynamics. Through the death of a star 5 times more massive than our Sun, different processes. Same result. Beauty so perfect it takes your breath away. That's number 5. The Butterfly Nebula, a cosmic insect with wings light years across. A dying star's final act of creation, proof that the universe is an artist, even, especially, in death. Number 4. The Crab Nebula. We've seen planetary nebulae, the deaths of sun-like stars. Beautiful, yes, but relatively gentle. Stars shedding their outer layers over thousands of years, creating glowing shells that slowly expand and fade. The Crab Nebula is different. This isn't a gentle death. On July 4th, 1054 AD, Chinese astronomers recorded the appearance of a guest star in the constellation Taurus. It was bright enough to be visible during the day. For 23 days, it outshone every object in the night sky except the moon. Slowly, over months, it faded from visibility. Japanese and Arab astronomers also recorded it. Native American rock art may depict it, but European records are strangely silent, possibly because Europe was in the Dark Ages and astronomical observation was limited. What those ancient observers witnessed was a supernova. A star that had exhausted its nuclear fuel, whose core collapsed in a fraction of a second, whose outer layers rebounded and exploded outward at 10% the speed of light. The explosion released more energy in a few seconds than the Sun will emit in its entire 10 billion year lifetime. And what remained? The Crab Nebula. When we look at the Crab Nebula today, we're seeing it roughly 1,000 years after the light from the explosion reached Earth in 1054 AD. The actual explosion happened about 6,500 years ago. But since the nebula is 6,500 light-years away, we're seeing the aftermath about a millennium after medieval astronomers first witnessed the supernova. We see a glowing, chaotic tangle of filaments. It looks nothing like the symmetric planetary nebulae we've discussed. There's no perfect sphere, no butterfly wings, no elegant structure. It's a mess. Shredded gas expanding in all directions. Filaments of different colors, red, blue, green, intertwining, crossing over each other, creating patterns that seem random but hint at underlying structure. The nebula is about 11 light-years across and still expanding at approximately 1,500 kilometers per second, over 5 million kilometers per hour. That's 0.5% the speed of light. Fast enough that astronomers can measure the expansion over decades, watching the nebula grow year by year. The colors tell a story. The red filaments are hydrogen, the star's outer atmosphere, blown away in the explosion. The blue glow comes from something different. Synchrotron radiation. At the center of the nebula is a pulsar, a neutron star, the collapsed core of the original star, compressed to a sphere only 20 kilometers across but containing 1.4 times the Sun's mass. This pulsar rotates 30 times per second. 30 complete rotations every second. Its magnetic field is incredibly powerful, trillions of times stronger than Earth's. And as it rotates, it acts like a cosmic lighthouse, beaming radiation out along its magnetic poles. This rotation and magnetic field generate a powerful wind of high-energy particles, electrons and positrons accelerated to near light speed. These particles spiral around magnetic field lines, emitting synchrotron radiation, a blue glow that fills the interior of the nebula. The Crab Nebula isn't just glowing from heat, it's powered, like a giant cosmic light bulb, with the pulsar as the filament, pumping energy into the surrounding gas, keeping it bright and active. If the pulsar ever stopped, if its rotation slowed to zero, the nebula would fade within a few decades. But pulsars lose rotational energy very slowly. The Crab pulsar will continue spinning for millions of years. Hubble images of the Crab Nebula reveal extraordinary complexity. You can see wave-like structures where the pulsar wind slams into the surrounding gas, creating shock waves. You can see knots and condensations, denser clumps that survived the initial explosion. You can see the central region glowing brilliant blue like an eye at the heart of chaos. And if you watch the nebula over months or years with high-resolution telescopes, you can see it change. Filaments shift, bright regions move. The inner structure evolves as the pulsar wind blows bubbles and creates new shocks. The Crab Nebula is alive, dynamic, constantly changing. It's not a static painting, it's a movie, a performance happening in real time across light years of space. And here's what makes it number 4. It represents transformation. A massive star lived for perhaps 10 million years, fusing hydrogen, helium, carbon, oxygen, neon, silicon, working its way up the periodic table, creating heavier and heavier elements in its core. When it reached iron, fusion stopped. Iron doesn't release energy when fused. It absorbs it. The core collapsed. The star exploded. And from that violence emerged this. A glowing nebula powered by a spinning neutron star, seeding the galaxy with heavy elements, creating raw material for future generations of stars and planets. Destruction and creation. Death and rebirth. The star died so that new stars and new worlds could be born. You're looking at the universe recycling itself, turning old stars into new possibilities, converting death into raw material for life. The Crab Nebula is beautiful, that the universe doesn't waste anything, that even in explosions, even in chaos, there's structure and meaning and beauty. That's number 4, the Crab Nebula. Frozen mid-explosion, still expanding after nearly a millennium. A monument to transformation. A reminder that endings are also beginnings. We've journeyed from planetary rings to planetary nebulae. From storms raging for centuries to explosions echoing for millennia. From our solar system to clouds of gas light years across. But we're only halfway through our countdown. And the objects ahead operate at scales that make nebulae look small. Scales where single objects contain not millions or billions of stars, but trillions. We're about to enter the realm of galaxies. Entire star cities. Islands of light separated by oceans of darkness. The beauty is about to become overwhelming. Let's continue. Number 3. The Andromeda Galaxy. We've left behind individual stars, nebulae, and stellar remnants. Now we zoom out to a scale so vast that entire nebulae become invisible specks. We're looking at galaxies, island universes, star cities containing hundreds of billions of suns separated from each other by millions of light years of nearly empty space. And the closest major galaxy to our own Milky Way is Andromeda. Catalogue designation M31. Messier 31, named after the French astronomer Charles Messier, who catalogued it in 1764. Though humans have observed it for thousands of years, ancient Persian astronomers called it the Little Cloud. It appears as a faint, fuzzy smudge in the night sky, visible to the naked eye on dark nights, located in the constellation Andromeda. For centuries, no one knew what it was. A nebula, perhaps. A cloud of gas within our own stellar system. It wasn't until the 1920s that Edwin Hubble, using the 100-inch Hooker telescope on Mount Wilson, resolved individual stars within Andromeda and calculated its distance. 2.5 million light-years away. That number is almost meaningless to human comprehension. Let me try to make it visceral. The light you see when you look at Andromeda left that galaxy 2.5 million years ago. When those photons began their journey, Earth was in the Pliocene epoch. Early hominids, Australopithecus, were just learning to use stone tools. Homo sapiens didn't exist yet. Wouldn't exist for another 2.2 million years. The light travelled through the void, through the space between galaxies, where there's almost nothing, less than 1 atom per cubic meter. It traveled for 2.5 million years at the speed of light, crossing distances so vast that our fastest spacecraft couldn't traverse them in millions of human lifetimes. And then, on some random night, when you happened to look up, that photon entered your eye. It struck a rod cell in your retina. It triggered a cascade of chemical reactions. It became a signal traveling along your optic nerve to your brain's visual cortex. And you perceived a faint smudge of light. Andromeda. That's what you're seeing with your naked eye. Photons that are older than humanity finally completing their journey. But when we point telescopes at Andromeda, particularly Hubble and modern ground-based observatories, we see something far more spectacular. Andromeda is a spiral galaxy, similar in structure to our own Milky Way but larger. About 220,000 light-years in diameter, roughly twice the diameter of the Milky Way. Its mass is estimated at 1.5 trillion solar masses, nearly twice the mass of our galaxy. It contains approximately 1 trillion stars. Let that number sink in for a moment. 1 trillion. If you counted one star per second, 24 hours a day, it would take you 31,700 years to count them all. And that's just one galaxy. Telescopic images of Andromeda reveal exquisite structure. The central bulge glows yellow-white. Old stars, ancient red giants, and dying stars densely packed. This bulge contains hundreds of billions of stars in a relatively small volume. Surrounding the bulge, the spiral arms. Curved lanes of blue-white young stars, pink star-forming nebulae, and dark dust lanes that obscure background light. The arms aren't solid structures. They're density waves, regions where stars and gas bunch up temporarily due to gravitational effects, triggering star formation and creating the appearance of structure. The spiral pattern is logarithmic, the same mathematical curve found in nautilus shells, hurricane formations, and whirlpools. It's the signature of rotation, gravity, and angular momentum creating beauty through pure physics. Andromeda has companions. Two small satellite galaxies orbit it, M32 and M110, dwarf elliptical galaxies that are gradually being torn apart by Andromeda's gravity. Eventually, they'll be absorbed completely, their stars becoming part of Andromeda's halo. This is galactic cannibalism, and it's common. Most large galaxies grew to their current size by consuming smaller neighbors. The Milky Way is currently absorbing the Sagittarius dwarf elliptical galaxy, a process that's been ongoing for hundreds of millions of years. But here's what makes Andromeda number 3 on this list. What elevates it beyond just being a beautiful spiral galaxy? It's approaching us. Most galaxies in the universe are moving away from us due to the expansion of space. Their light is redshifted, stretched to longer wavelengths by the Doppler effect. But Andromeda is blue-shifted. It's moving toward the Milky Way at approximately 110 kilometers per second, nearly 400,000 kilometers per hour. In about 4 billion years, give or take a few hundred million, Andromeda and the Milky Way will collide. Not a collision of stars, galaxies are mostly empty space, and direct stellar collisions will be rare, but a collision of galaxies. The two systems will pass through each other, their gravitational fields interacting, their structures distorting. The first pass will pull long tidal tails of stars from both galaxies. The Milky Way's spiral arms will be disrupted. Andromeda's disk will warp and stretch. Gas clouds will collide, triggering enormous bursts of star formation, millions of new stars igniting across both galaxies simultaneously. Then, over hundreds of millions of years, the two galaxies will fall back together, merge, and eventually settle into a single elliptical galaxy, a spherical swarm of stars with no spiral structure. Astronomers have already named it Milkomeda. Simulations of this merger are breathtaking. You can watch the two galaxies approach, distort, tear streams of stars from each other, pass through, turn around under mutual gravity, and collide again and again until they merge. From Earth's perspective, if Earth still exists, if the Sun hasn't already expanded into a red giant and engulfed it, the night sky will become spectacular. Andromeda will grow larger and larger over millions of years. Instead of a faint smudge, it will become a defined spiral, then a brilliant band across half the sky, then a chaotic swirl of stars filling the entire celestial sphere. The sky will blaze with stars, blue-white giants born in the collision's star-forming regions. The galactic cores of both Andromeda and the Milky Way, each containing a supermassive black hole, will spiral toward each other, eventually merging into a single, even more massive black hole. It will be the most spectacular sky show Earth will ever experience, and it's inevitable, already in progress. The galaxies are rushing toward each other, and nothing can stop them. When you look at Andromeda tonight, you're not just seeing a beautiful galaxy. You're seeing our future, our destiny. The galaxy that will someday merge with ours, reshaping both into something new. You're watching the setup for a collision that will happen in 4 billion years, a collision whose light will take millions of years to complete, whose consequences will echo for billions of years afterward. Andromeda is beautiful because it's vast, because it contains 1 trillion suns, because its spiral arms trace perfect logarithmic curves. But it's also beautiful because it's personal. It's part of our story. The galaxy that will end the Milky Way as we know it and create something new, that's number 3. Andromeda, our nearest galactic neighbor, our future partner in the universe's greatest merger. 1 trillion stars rushing toward us at 110 kilometers per second, bringing beauty and transformation. Number 2, the Whirlpool Galaxy. If Andromeda shows us galactic beauty at a personal level, our future collision partner, then the Whirlpool Galaxy shows us galactic beauty at its most perfect catalogue designation, M51. Located approximately 23 million light-years away in the constellation Canis Venatici, the hunting dogs. The Whirlpool Galaxy is a spiral galaxy, like Andromeda and the Milky Way. But what makes it extraordinary, what makes it number 2 on this list, is that we see it face on. Most galaxies we observe are tilted at various angles. We see them edge on, or at oblique angles, which makes their spiral structure difficult to appreciate. But the Whirlpool, we see it from above, looking straight down onto the galactic disk. And the view is breathtaking. 2 perfect spiral arms emerge from the central bulge and wrap around the galaxy in smooth, elegant curves. The arms are bright blue-white, blazing with young stars and glowing pink nebulae. Active star-forming regions where new suns are igniting dark dust lanes trace the inner edges of the spiral arms, regions where dense molecular clouds block background light. These dust lanes are where stars will form in the future. Cold, dense gas, collapsing under gravity, fragmenting into clumps that will become stellar nurseries. The central bulge glows yellow-white. Old stars, ancient giants, the stellar population that formed early in the galaxy's history. This is the galactic core, densely packed with stars orbiting a supermassive black hole at the very center. And then there's the companion. At the end of one of the spiral arms, connected by a bridge of stars and gas, is NG C5195, a smaller, irregular galaxy being torn apart by the Whirlpool's gravity. This companion is being consumed. Its stars are being stripped away by tidal forces. Gas is being pulled from its body, streaming into the Whirlpool, triggering new waves of star formation in the spiral arms. The interaction is violent, but it's also beautiful. The bridge connecting the 2 galaxies glows faintly. Stars and gas stretch between them, creating a luminous thread linking the 2 systems. And that interaction is why the Whirlpool's spiral arms are so perfect. The companion's gravity creates tidal forces that compress gas in the Whirlpool's disk, triggering star formation and reinforcing the spiral structure. The arms aren't permanent features, they're density waves. Regions where stars and gas temporarily bunch up as they orbit, like cars bunching up in traffic. The wave pattern rotates at a different speed than the stars themselves, creating the appearance of structure. But the companion's gravity amplifies these waves, making them more prominent, more defined, more spectacular than they would be in an isolated galaxy. Hubble images of the Whirlpool reveal extraordinary detail. You can see individual star clusters, groups of hundreds or thousands of young blue stars born together from the same molecular cloud. You can see Cepheid variables, pulsating stars that astronomers use as standard candles to measure cosmic distances. You can see supernova remnants, glowing bubbles where massive stars exploded, leaving expanding shells of gas. You can see planetary nebulae, tiny, faint rings scattered throughout the galaxy, dying sun-like stars shedding their outer layers. And if you zoom in far enough, you can see the supermassive black hole at the center. Not directly, black holes emit no light, but you can see its effects. Stars orbiting at tremendous speeds around an invisible point, gas swirling in an accretion disk before crossing the event horizon and disappearing forever. The Whirlpool Galaxy contains approximately 100 billion stars. Not as many as Andromeda or the Milky Way, but still an incomprehensible number. Each star is a sun. Each might have planets. Some might have life. Imagine beings on a planet orbiting a star in the Whirlpool's outer arm, looking up at their night sky. They'd see the galactic core as a brilliant band of light. They'd see the spiral arms wrapping around them. They'd see the companion galaxy hanging in their sky, a smaller, irregular glow gradually being torn apart. And 23 million light-years away across the void, they might see our galaxy, the Milky Way, just a faint smudge of light, one galaxy among billions visible in their telescopes. The Whirlpool Galaxy is beautiful because it's perfect. The symmetry is almost too good to be true. The spiral arms trace mathematical curves. The star-forming regions glow like jewels embedded in the arms. The companion adds drama, a smaller galaxy being devoured, its death triggering beauty in its destroyer. It's proof that gravity can create art, that physical laws produce aesthetics, that the universe, left to its own devices, sculpts beauty. The Whirlpool Galaxy shows us what the Milky Way looks like from outside. We can't see our own galaxy's spiral structure. We're inside it, embedded in the disk, seeing only the edge-on view of a band stretching across the sky, but the Whirlpool gives us the view we can never have of our own home. And it's gorgeous. When you look at the Whirlpool Galaxy, you're seeing ourselves, our cosmic address. The structure we inhabit, revealed in another galaxy 23 million light-years away. You're seeing proof that we live in something this beautiful, that our galaxy, our home, is just as spectacular as this, if only we could step outside and look back. That's number 2. The Whirlpool Galaxy. Spiral perfection. A cosmic pinwheel spinning through space, devouring its companion, creating stars, sculpting beauty through gravity alone. But there's still one object left. One image that surpasses even galactic perfection. One photograph that changed how we see the universe forever. Let's finish the countdown. Number 1. The Hubble Deep Field. This is it. The most beautiful, most important, most profound astronomical image ever captured. Not because it shows one beautiful object, but because it shows thousands. Let me tell you the story of this image, because the story is part of what makes it extraordinary. In 1995, astronomer Robert Williams was director of the Space Telescope Science Institute, the organization that operates the Hubble Space Telescope. He had director's discretionary time, the ability to point Hubble at any target he wanted for a certain number of observing hours. He made a controversial decision. Instead of observing a known object, a specific galaxy, nebula or star, he decided to point Hubble at nothing. An empty patch of sky, a tiny region near the Big Dipper with no bright stars, no known galaxies, nothing of interest. A piece of sky that appeared completely blank to ground-based telescopes. He pointed Hubble at this empty region and told the telescope to stare. For 10 consecutive days, 342 separate exposures. Over 100 hours of total exposure time. Many astronomers thought it was a waste of time. Why spend precious Hubble time staring at nothing when there were so many known targets to observe? But Williams had a hypothesis. Based on cosmological theories, he suspected that even empty space contained distant galaxies too faint for ground-based telescopes to detect. He wanted to see how deep Hubble could see, how far back in time it could peer. The data came back, and it was shocking. That empty patch of sky contained nearly 3,000 galaxies, not stars, not nebulae, galaxies, each one containing billions of stars, each one millions or billions of light years away. The image, called the Hubble Deep Field, was released in January 1996, and it changed astronomy forever. Let me describe what you see in this image. The field of view is tiny, about 1/24 millionth of the entire sky. If you held a grain of sand at arm's length, it would cover the same apparent area as the Hubble Deep Field. That tiny patch of sky contains nearly 3,000 galaxies extrapolate across the entire sky, 200 billion galaxies in the observable universe. Each point of light in the Hubble Deep Field is a galaxy, not a star, a galaxy, an entire island universe containing hundreds of billions of stars. Some of the galaxies are spiral, grand designs like the Whirlpool or Andromeda. Some are elliptical, smooth, featureless ovals. Some are irregular, chaotic, disrupted by collisions or tidal interactions. Some are so distant they're just faint smudges. Proto-galaxies still forming in the early universe. The colors indicate distance. Blue galaxies are relatively nearby. Their light hasn't been significantly redshifted by the expansion of space. Red galaxies are farther. Their light stretched to longer wavelengths by billions of years of cosmic expansion. The faintest galaxies in the image had, at the time of observation, traveled over 12 billion years to reach us, pushing back to when the universe was less than 2 billion years old. While the James Webb Space Telescope has since observed even more distant galaxies, the Hubble Deep Field remains the iconic image that first revealed the universe's true depth. We're seeing them as they were when the universe was less than 2 billion years old, still in its infancy, still forming the first generations of stars. Think about that. You're looking at light that left those galaxies before Earth existed, before the Sun formed, before the Milky Way had fully assembled. You're seeing the universe as it was when it was young, chaotic, still organizing itself, and you're seeing it in a patch of sky the size of a sand grain. The Hubble Deep Field doesn't just show us beauty, it shows us scale. It shows us our place in the cosmos with brutal honesty. Every galaxy in that image contains billions of stars. Each star might have planets. Some planets might be habitable. Some might host life. Some might have civilizations looking up at their skies, seeing our galaxy as a faint smudge among thousands, wondering if they're alone. Multiply that by 200 billion galaxies across the entire sky. The numbers become meaningless. The scale becomes incomprehensible. Your brain simply can't process it. And that's the point. The Hubble Deep Field is beautiful because it humbles us. It shows us that we're not just small, we're incomprehensibly small. Our Sun is one of about 200 billion stars in the Milky Way. The Milky Way is one of 200 billion galaxies in the observable universe. That means there are roughly 10 sextillion stars in the observable universe. That's 10,000 trillion stars, each one a sun, each one potentially with worlds, some with life, some with intelligence, some with civilizations that rose and fell billions of years ago, whose light is still traveling toward us, carrying messages we'll never decode because the senders are long extinct. The Hubble Deep Field is the ultimate existential image. It shows us we're tiny, insignificant, a fleeting moment in cosmic time, a single species on a single planet orbiting a single star in a single galaxy among billions. But it also shows us we're part of something vast and ancient and beautiful. We're connected to those distant galaxies through the laws of physics. The same gravity, electromagnetism, nuclear forces that govern them govern us. The atoms in our bodies were forged in stars in our own galaxy, siblings to the stars in those distant galaxies. We're not separate from the universe. We're made of it. We're the universe becoming conscious of itself. We're the cosmos waking up and looking back at its own structure with wonder. The Hubble Deep Field doesn't show one beautiful object. It shows everything. The entire visible universe concentrated in a single image, depth beyond measure, time beyond comprehension, beauty beyond description. That's why it's number one. Not because it's the prettiest image, though it is stunning in its own way, but because it's the most meaningful image, the most profound, the most humbling and inspiring at the same time. When you look at the Hubble Deep Field, you're not just seeing galaxies, you're seeing infinity. You're seeing your cosmic context. You're seeing the neighborhood you belong to. Not the solar system, not the Milky Way, but the universe. You're seeing home. We've completed the countdown. From Saturn's rings in our cosmic backyard to galaxies billions of light years away, from objects we can visit with spacecraft to structures we can only dream of reaching. 10 objects, each beautiful in its own way, each teaching us something about physics, time, scale, and existence. But now I want to talk about what it all means, not scientifically, but personally. What does beauty in the cosmos teach us about ourselves? Let's bring this journey home. Before we talk about what all this beauty means, I need to mention a few objects that didn't make the top 10. Not because they're not beautiful, but because they represent a different kind of beauty. Not aesthetic perfection, but extremes. The universe at its most powerful, most alien. These are honorable mentions. Objects so extreme they redefine what beautiful even means. The black hole shadow. M87 star. In April 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole's shadow. Not the black hole itself. Black holes emit no light. But the shadow. The silhouette of the event horizon against the glowing accretion disk surrounding it. The image shows a bright orange ring, superheated matter swirling around the black hole at near light speed, with a dark circle in the center. That darkness is the event horizon, the point of no return where gravity becomes so strong that not even light can escape. The black hole is M87 star, located at the center of the giant elliptical galaxy M87, about 55 million light-years away. Its mass is 6.5 billion times the mass of our Sun. The event horizon itself is about 20 billion kilometers across, and the dark shadow we see in the image, which appears larger due to light bending around the black hole, is roughly 40 billion kilometers in diameter, larger than the orbit of Neptune in our solar system. The accretion disk glows because matter falling toward the black hole is compressed and heated to billions of degrees. As it spirals inward, it emits X-rays, ultraviolet light, and radio waves. Some of this matter doesn't fall in. It's flung outward in jets that extend for thousands of light years, moving at 99% the speed of light. The image is beautiful because it shows something invisible. We're seeing the absence of light, a hole in space-time. a region where the laws of physics break down, where time itself stops at the event horizon, where the curvature of space becomes infinite. It's the universe showing us what happens when gravity wins completely, when matter is crushed so densely that it vanishes from the observable universe, when the fabric of reality itself tears. And that orange glow, matter swirling around the abyss, glowing with its last light before crossing the point of no return, is hauntingly beautiful, a funeral pyre at the edge of oblivion. Neutron star collision, GW 170817. On August 17, 2017, gravitational wave detectors LIGO and Virgo recorded a signal unlike anything they'd detected before. Not the collision of two black holes, those produce sharp, quick bursts. This signal was longer, more complex, sweeping upward in frequency over about 100 seconds. Two neutron stars, dead stellar cores, each about 20 kilometers across but containing more mass than the Sun, were spiraling toward each other. As they orbited, they emitted gravitational waves, ripples in space-time itself, carrying away energy and angular momentum. The orbit decayed, the neutron stars moved closer and closer, orbiting faster and faster, emitting waves at higher and higher frequencies. The signal swept upward like a cosmic chirp, and then, suddenly, merger. The neutron stars collided at a significant fraction of the speed of light. The collision released more energy in gravitational waves than the Sun will emit as light in its entire 10 billion year lifetime. But that wasn't all. The collision also released electromagnetic radiation, a kilonova. Telescopes around the world swung toward the source, located in galaxy NGC 4993, about 130 million light-years away. What they saw was extraordinary. A rapidly fading fireball glowing blue, then red, expanding outward from the collision site. This wasn't just an explosion, it was a forge. When neutron stars collide, they create conditions of extreme temperature and density. Hot enough, dense enough to forge heavy elements. Gold, platinum, uranium. All the elements heavier than iron that can't be made in normal stellar fusion. All the gold on Earth, in jewelry, in electronics, in your phone, was created in neutron star collisions billions of years ago. The shockwave from those ancient collisions seeded the molecular cloud that eventually collapsed to form our solar system. You're wearing the debris of dead stars. Your wedding ring is neutron star shrapnel. The beauty here isn't visual. The images of the kilonova are just faint, fuzzy blobs. The beauty is conceptual. It's the realization that the universe forges precious metals, that the rarest elements on Earth are born from stellar death. That destruction creates the raw materials for beauty. Saturn's hexagon. Return briefly to Saturn, because there's one feature we didn't discuss. The hexagon at Saturn's north pole. This is one of the strangest atmospheric features in the solar system. A near-perfect six-sided storm at the North Pole, rotating with the planet's interior. Each side of the hexagon is about 13,800 kilometers long, wider than Earth's diameter. It's been there since at least 1981, when Voyager first photographed it. Cassini observed it from 2004 to 2017, watching it change with Saturn's seasons. During southern summer, the hexagon appeared golden brown. As northern spring arrived, it shifted to blue gold. But the shape persists. A perfect hexagon. 6 straight sides meeting at nearly exact angles, rotating once every 10 hours and 39 minutes, slightly faster than Saturn's deeper atmosphere, but slower than its cloud tops. Why hexagonal? Nobody knows for certain. The leading theory involves Rossby waves, atmospheric waves that can create polygonal patterns under certain conditions. Laboratory experiments have reproduced hexagonal vortices in rotating fluids. But on Saturn, the scale is planetary. The hexagon is larger than Earth. It's beautiful because it's geometry. Nature, creating perfect mathematical forms at scales that dwarf our entire world. The universe revealing its deep mathematical structure in atmospheric flow patterns on a gas giant billions of kilometers away. The cosmic web. Large-scale structure. Finally, zoom out farther than we've gone before. Farther than individual galaxies. Farther than galaxy clusters. Look at the universe on the largest scales, billions of light years across, and you see structure. Galaxies aren't randomly distributed through space. They're organized into a vast cosmic web, filaments of galaxies stretching hundreds of millions of light years, connecting at nodes where galaxy clusters reside between the filaments. Voids. Vast empty regions nearly devoid of galaxies. The pattern looks organic, like neurons in a brain, like mycelium in soil, like the circulatory system in a body, branching, interconnecting, hierarchical. This structure formed from tiny density fluctuations in the early universe. Regions that were slightly denser than average attracted more matter through gravity. Over billions of years, these small differences amplified. Matter flowed along gravitational gradients, creating the filaments we see today. Dark matter, the invisible substance that makes up 85% of the universe's matter, forms the scaffolding. Galaxies form where normal matter accumulates along dark matter filaments. Maps of the cosmic web, created by plotting millions of galaxies' positions, are stunningly beautiful. They look like abstract art, like neural networks, like the universe is thinking. And maybe it is, in a way. We're part of this structure. Our consciousness emerged from matter organized by these same gravitational forces. We're the cosmic web becoming aware of itself. The beauty here is in pattern. In realizing that the universe is organized on every scale, from atoms to superclusters, that structure emerges naturally from physical law. That chaos gives birth to order. These honorable mentions show us that beauty isn't just symmetry and color, it's also extremes. Black holes, neutron-star collisions, geometric storms, cosmic structure. The universe is beautiful, in its scale, in its strangeness, in its refusal to be ordinary. We've seen 10 objects plus several honorable mentions. Rings and storms, nebulae and galaxies, black holes and collisions. Each one beautiful in its own way. But step back and look at the pattern. Look at what all these objects have in common. They all follow mathematical rules. Saturn's rings obey Kepler's laws of orbital mechanics. Every ice particle orbits according to precise equations relating mass, distance, and velocity. Jupiter's Great Red Spot is a solution to the Navier-Stokes equations governing fluid dynamics. The storm's structure emerges from differential rotation, Coriolis forces, and turbulent convection. The aurora follows Maxwell's equations. Charged particles spiral along magnetic field lines, their paths determined by the Lorentz force. The pillars of creation show the results of photoevaporation, a process where radiation pressure and thermal expansion compete with gravity. The shapes emerge from the balance of these forces. Planetary nebulae form when red giants shed their envelopes, creating structures governed by hydrostatic equilibrium, radiation pressure, and magnetic fields. Spiral galaxies trace logarithmic spirals, the same mathematical curve found in nautilus shells, hurricanes, and sunflower seed patterns. This spiral appears whenever rotation, growth, and geometry combine. The Hubble Deep Field reveals the large-scale structure of the universe, shaped by dark matter, dark energy, and gravitational amplification of quantum fluctuations from the Big Bang. Every beautiful object in the universe follows laws, physical principles that can be written as equations, simulated on computers, tested through observation. And here's what's profound. The equations don't know they're creating beauty. Newton's laws don't care if orbits are aesthetic. The Schrödinger equation doesn't aim for symmetry. Maxwell's equations don't strive for elegance. Yet beauty emerges. Automatically. Inevitably. Why? Here's my hypothesis. Beauty is the signature of physics working correctly. When physical systems reach stable, low-energy states, they naturally exhibit symmetry, pattern, and harmony. When systems evolve according to mathematical laws, they generate structures that appear designed. Symmetry appears because physical laws are symmetric. Gravity doesn't prefer one direction over another, so planets are spheres. Angular momentum conservation creates rotation, which creates spiral patterns. Energy minimization creates close-packed structures. The universe is fundamentally mathematical, and mathematics is inherently aesthetic. Euler's identity, a to the power of I pi plus 1 equals 0, is considered one of the most beautiful equations in mathematics because it connects 5 fundamental constants in a simple, elegant relationship. The same principle applies to cosmic objects. They're beautiful because they're solutions to equations, optimal states, natural consequences of physical law. The universe isn't trying to be beautiful. It just is. Beauty is built into the fabric of reality at the deepest level, and we recognize it because we're pattern recognition machines. Our brains evolved to detect symmetry, contrast, harmony, and structure, all signals of order in a complex world. When we see Saturn's rings, we're recognizing mathematical perfection. When we see the Whirlpool Galaxy, we're detecting logarithmic spirals. When we see the Hubble Deep Field, we're comprehending vast scales organized by gravitational law. We're not projecting beauty onto the cosmos. We're discovering beauty that's already there. Beauty that existed before humans evolved. Beauty that will remain after we're gone. The universe is a gallery, physics is the artist, and mathematics is the language in which beauty is written. But here's the humbling part. Everything I've shown you represents a tiny fraction of what's out there. Human eyes evolved to detect wavelengths between 380 and 750 nanometers. The visible spectrum, red to violet. The colors of sunlight. But the electromagnetic spectrum extends far beyond visible light. Radio waves with wavelengths measured in meters, microwaves. Infrared. On the other side, ultraviolet. X-rays, gamma rays with wavelengths smaller than atoms. Most of the universe is invisible to human eyes. When you look at images from Hubble, or JWST, or Chandra, you're not seeing real colors. You're seeing false color. Wavelengths beyond human perception translated into colors we can see, the pillars of creation's famous colors. That's infrared and ultraviolet mapped to red, green, and blue. The real pillars in visible light alone are far dimmer, less colorful, harder to see. The Crab Nebula's blue glow, that's synchrotron radiation, a type of light produced by relativistic electrons spiraling in magnetic fields. It occurs across the spectrum, from radio to X-rays. The images we see combine multiple wavelengths. The Hubble Deep Field, those distant galaxies are so redshifted that much of their light has moved out of visible wavelengths into infrared. Hubble can see them, but barely. The James Webb Space Telescope, designed for infrared, sees them far more clearly. The universe contains beauty we can't perceive. Colors we can't see, structures invisible to our eyes, phenomena beyond our senses. Every new wavelength we observe reveals new beauty. When X-ray telescopes first observed the sky, they discovered jets, coronae, black hole accretion disks, structures utterly invisible in visible light, but stunning in X-rays. When radio telescopes mapped the sky, they found pulsars, quasars, radio galaxies, objects that barely register in optical surveys, but dominate in radio wavelengths. When infrared telescopes peered through dust clouds, they revealed star-forming regions hidden from visible light telescopes. They showed us the cores of galaxies obscured by dust. They let us see through the cosmic dust that blocks optical light. and the James Webb Space Telescope, launched in December 2021 and operational since mid-2022, designed primarily for infrared, is revealing even more. JWST can see the first galaxies that formed after the Big Bang, so distant and redshifted that Hubble could barely detect them. It can see through the dust of star-forming regions to watch planets being born. It can characterize exoplanet atmospheres in unprecedented detail. Every improvement in technology reveals more beauty, more structure, more complexity. And we're just beginning. The telescopes we have today are limited by engineering, not by physics. We can build larger mirrors, more sensitive detectors, space-based observatories free from atmospheric distortion. Future telescopes. The extremely large telescope, with its 39-meter mirror, the proposed Habitable Worlds Observatory, maybe even interferometers spanning the solar system, will reveal details we can barely imagine. We might directly image the surfaces of exoplanets, sea continents and oceans on worlds light years away, detect biosignatures, oxygen, methane, atmospheric chemistry, indicating life-watch weather patterns on alien worlds. We might map the cosmic web in 3 dimensions with billions of galaxies. See how structure formed over cosmic time. Trace the flow of matter along dark matter filaments. We might observe the event horizons of black holes in multiple wavelengths, watching matter spiral inward, jets launch outward, space-time warp and twist. The beauty we've seen so far. It's a preview, a teaser. The universe has barely begun showing us what it can do. Imagine what we'll discover in the next century, the next 1,000 years, the next 1,000,000 years, if humanity survives that long. Every wavelength reveals new beauty. Every improvement in resolution shows more detail. Every advance in technology expands our cosmic vision. The universe is more beautiful than we can currently perceive. And we're slowly, gradually, painfully building the eyes to see it. We've journeyed from Saturn to the edge of the observable universe. From objects we can visit to structures billions of light years across. From beauty we can see with naked eyes to beauty revealed only by the most sophisticated instruments humanity has ever built. But what does it all mean? Not scientifically, we've covered the physics, but personally, emotionally, philosophically. What does cosmic beauty teach us about existence, meaning, and our place in the universe? Let's finish this journey by bringing it home to you, to us, to what it means to be conscious beings in a beautiful cosmos. We've seen the most beautiful objects in the universe. Now let's talk about what that beauty means. Here's the first profound truth. Beauty doesn't need observers to exist. The pillars of creation were beautiful for 6,500 years before humans invented telescopes powerful enough to see them. They were beautiful when our species was living in caves. They were beautiful when Earth was dominated by dinosaurs. They were beautiful when life on Earth was single-celled. Bacteria floating in ancient oceans. The Whirlpool Galaxy was spinning its perfect spiral arms for millions of years before any conscious being looked up and appreciated it. Saturn's rings were gorgeous long before Galileo pointed his telescope at them. Beauty is intrinsic to the universe. It's not something we project onto nature, it's something we discover in nature. The universe creates beauty automatically. As a byproduct of physical law, gravity sculpts galaxies. Nuclear fusion creates colors in nebulae. Orbital mechanics arranges rings. Mathematical equations generate fractals, spirals, and symmetries. None of these processes care about aesthetics. They're just following the laws of physics. And yet, beauty emerges. This tells us something profound. The universe is fundamentally ordered. It follows rules. Those rules generate pattern, structure, harmony. And we, conscious beings who evolved pattern recognition systems, perceive that order as beauty. But here's the second profound truth. While beauty doesn't need observers, It's exponentially more meaningful because of observers. We are the universe becoming conscious of itself. We're stardust organized into patterns complex enough to appreciate beauty. We're atoms forged in dying stars, assembled into brains that can comprehend spiral galaxies and quantum mechanics. Carl Sagan said, "We are a way for the cosmos to know itself." That's not poetic hyperbole, it's literally true. For 13.8 billion years, the universe existed without consciousness. At least in our cosmic neighborhood, stars formed, lived, and died. Galaxies collided, nebulae glowed, black holes devoured matter, all beautiful, all spectacular, all unobserved. And for the first time in cosmic history, at least in this region of space, the universe could look at itself and experience wonder. When you look at the Hubble Deep Field, you're not separate from it, you're part of it. The atoms in your body came from stars in galaxies like those. The iron in your blood was forged in a supernova. The calcium in your bones came from dying stars. The oxygen you breathe was created by stellar fusion. You are not in the universe. You are the universe. A temporary pattern, yes. A brief organization of matter that will eventually dissolve back into simpler forms. But while you exist, you're the cosmos experiencing itself. And that makes beauty matter. Not just objectively existing, but subjectively experienced, felt, appreciated, understood. This is why we explore, why we build telescopes, why we send spacecraft to distant planets, why we spend billions of dollars photographing galaxies millions of light years away. Not just for scientific knowledge, though that's valuable, but because we're drawn to beauty, because we need to see it, understand it, share it. Art, science, exploration, they're all driven by the same impulse. The desire to find and create beauty. To make sense of the universe, to connect with something larger than ourselves. When ancient humans looked up at the night sky and told stories about constellations, they were doing the same thing we do when we publish Hubble images, trying to make meaning from the cosmos, trying to understand our place in it. The tools have improved. We have telescopes instead of naked eyes, spacecraft instead of campfire stories. But the impulse is the same. We're meaning-making creatures, and beauty is how we recognize meaning in the universe. So here's what I want you to do. Tonight, definitely tonight, go outside and look up. If you live in the Northern Hemisphere, look south during autumn or winter evenings. Find the brightest star in the sky, that brilliant blue-white point that outshines everything around it. That's Sirius, number 10 on our list, 8.6 light-years away. A binary system where one star has already died. The light you see left that star in 2016. Look northwest during evening hours and you might see Jupiter, a brilliant star that doesn't twinkle like true stars do. Through binoculars or a small telescope, you can see Jupiter's cloud bands. Maybe, if conditions are good, the Great Red Spot, number 9 on our list. A storm larger than Earth, raging for centuries. If you're in the southern hemisphere, look toward the constellation Centaurus. Find the third brightest star in the night sky, Alpha Centauri, our nearest stellar neighbor. Near it, invisible to your naked eye, is Proxima Centauri with its potentially habitable planet, the closest world beyond our solar system. And if you're away from city lights, if the sky is dark enough, look for the Milky Way. That cloudy band stretching across the sky, you're seeing our galaxy edge on billions of stars, nebulae, star clusters. All of it too distant to resolve as individual points, blending into a luminous river. That's your cosmic address. You're inside that band of light. One of 200 billion stars in a spiral galaxy 100,000 light-years across. And if you have binoculars or a small telescope, point them toward Andromeda. That faint smudge becomes larger, more defined. You can see its oval shape. Maybe, if your equipment is good enough, hints of its spiral structure. You're seeing a galaxy of 1 trillion stars, light that left 2.5 million years ago, a galaxy rushing toward us, destined to collide with ours in 4 billion years. All of this, Sirius, Jupiter, the Milky Way, Andromeda, visible to you, tonight, from your backyard or a nearby dark sky location. You don't need a professional observatory, you don't need expensive equipment. You just need to look up. And if you can't see these objects, if clouds block your view, if light pollution washes out the stars, then go online, NASA's website, ESA's Hubble Gallery, JWST's image releases. They're free. All of them. High-resolution images of the most beautiful objects in the universe, available to anyone. Download them. Set them as your phone wallpaper. Print them and hang them on your wall. Look at them. Really look. Don't just scroll past pause. Zoom in. Read the captions. Understand what you're seeing. Let the scale sink in. Let the beauty affect you. Because this isn't just education, it's inspiration. It's connection to something vast and ancient and ongoing. It's remembering that you're part of the cosmos, not separate from it. The universe isn't cold and distant. It's here, in you, around you, above you. You're made of stardust. That's not metaphor. That's chemistry. The atoms in your body, every single one except hydrogen, were forged in stars. Carbon from red giants, oxygen from massive stars, iron from supernovae, gold from neutron star collisions. You are the universe's way of experiencing itself. You are consciousness, emerging from matter. You are beauty, recognizing beauty. Never forget that. We've journeyed through the most beautiful objects in the universe. From Saturn's rings to the Hubble Deep Field. From storms and nebulae to galaxies and cosmic structure. 10 objects, each extraordinary, each teaching us something about physics, scale, time, and existence. But here's what I want you to take away from this journey. Beauty is everywhere. Not just in the cosmos, but here, on Earth, in nature, in human creations, in mathematics and music and art. The same principles that create spiral galaxies create hurricanes on Earth. The same mathematics that describes orbital mechanics describes how planets form and how birds fly. The same physics that powers stars powers every living cell. The universe is unified, governed by the same laws at every scale, in every location, at every time. And those laws produce beauty automatically. When you see a sunset, you're seeing light scattering through Earth's atmosphere, the same phenomenon that makes nebulae glow. When you see a rainbow, you're seeing light refracted and separated by wavelength, the same process astronomers use with spectrographs to analyze starlight. When you see a spiral seashell, you're seeing the same logarithmic spiral that appears in galaxies. When you see branching rivers or lightning, you're seeing fractal patterns that appear in cosmic structure. Beauty isn't rare, it's fundamental. It's built into the fabric of reality, and consciousness, your consciousness, allows that beauty to be appreciated. So don't just reserve wonder for cosmic objects, bring that same sense of awe to everyday life. Look at trees and see fractal branching. Look at snowflakes and see crystalline symmetry. Look at waves on a beach and see fluid dynamics in action. The universe is beautiful, all of it, from galaxies to atoms, from the largest structures to the smallest. And you get to experience it. You get to understand it. You get to share it. That's not a small thing. That's everything. You exist against impossible odds. In a universe vast beyond comprehension, on a planet perfectly suited for life, with a brain capable of appreciating beauty and understanding physics, you are the universe looking at itself and feeling wonder. Don't waste that. Don't spend your life scrolling through distractions without pausing to appreciate the miracle of existence. Look up, look around, look, really look. See the beauty that's always been there, waiting for conscious beings to notice it. And remember, you're not separate from this. You're not an observer watching from outside. You are the cosmos, temporarily organized into a pattern capable of thought, a brief eddy in the flow of matter and energy. But while you exist, you're part of the universe's story. Make it beautiful. Make it meaningful. Make it matter. Because in the end, that's what beauty teaches us. Things don't have to last forever to be worthwhile. Saturn's rings will disappear in 100 million years. The great red spot is shrinking. The pillars of creation are already destroyed. Andromeda and the Milky Way will eventually merge and lose their spiral structure. Even the galaxies themselves will someday fade as the universe expands and stars exhaust their fuel. But right now, they're beautiful, and that's enough. You don't have to be eternal to be meaningful. You don't have to last forever to matter. You just have to be, fully, consciously. With wonder and appreciation, the universe is beautiful. And so are you. If you've made it this far, thank you, truly. You've just traveled from our solar system to the edge of the observable universe. You've seen rings, storms, nebulae, galaxies, black holes, and cosmic structure. You've contemplated scale, time, physics, and meaning. Not just Earth, not just the solar system, but all of it, the entire cosmos, your inheritance, your context, your home. We're not isolated on a small planet in an empty void. We're part of something vast and interconnected, a universe that creates beauty automatically, a cosmos that's fundamentally ordered, mathematical, aesthetic. And we get to witness it, to understand it, to share it. That's the privilege of consciousness. That's the gift of being alive in this time, with these tools, with this knowledge. Subscribe if you want more journeys through the cosmos. Comment with which object was most beautiful to you. Was it Saturn's rings, the pillars of creation, the Hubble Deep Field, or something else? Share this video with someone who needs to be reminded that they're part of something extraordinary, with someone who's lost their sense of wonder, with someone who needs to see beauty. And tonight, definitely tonight, look up, find Sirius. Find the Milky Way, find Andromeda if you can. Or just look at the stars and remember, you're looking at suns. Distant, yes, but real. Some with planets, some possibly with life. The universe is beautiful. You're part of it. And that makes you beautiful too. Welcome to the cosmos. It's been waiting for you.